I hope you're seeing some good stuff today. These are some cut and dry kind of examples of how the math we teach in those entry-level courses is useful to you on an everyday basis. What I'm going to talk to you about right now is kind of setting up for what we're going to do throughout the rest of this. I want to talk about the quadratic formula, and I'm not going to focus so much on examples right now, but I do want to justify why we teach this crazy thing and why it's important to us to know it. And in fact, I'm not even going to prove the thing. I'm counting on your teacher to do those kind of nuts and bolts kind of things. But what I want to get across to you is why we need to know this ridiculous formula. I mean, if you've seen this, it's kind of messy. And those of us who've been in math a long time, we have it burned into our brain. You know, we don't have to remember it, it's there. But there's a purpose behind knowing that, and I want to kind of get into that today. We have talked about things in the past that had this form, and let me kind of flash this up. Some constant and then x minus m times x minus n. Okay, now this would be a quadratic equation because when I FOIL this out, I'm going to get an x squared term. Well, we talked about in the past how this has solutions at x equals m. That makes sense. If I plug in m here, I get 0 times the rest of it. 0 times anything is 0. Same deal with the n. If I plug in an n, multiply this out, it's 0 times everything else, so I get a 0. Okay? We also discussed how not every quadratic equation, this is the more kind of general form of the quadratic equation, we can't always write things like this, like that. And that's a difficulty. We start out solving quadratic equations by factoring, but there's a lot of things that simply cannot be factored. Okay? For two reasons. One of the reasons is the parabola that would be the graph of this quadratic function may not cross the x-axis. Let me just kind of set this in motion. What I've done here is I've taken a general parabola and I've juked around some of the parameters, if you will, to kind of show. And here you're looking at some where they do cross the x-axis, and there you're looking at some where they don't. Okay? Let's see if I can flash that back. Don't. There it crosses twice, and then eventually it'll kind of move up. At some point it crosses just once, and then it doesn't cross at all. And even worse than that, many of those that do cross the x-axis, the second problem is many of those that do cross the x-axis can't be factored. I'll give you an example. Here's one where I can't actually solve for the zeros. If I look at this equation, I need two factors of 6 that differ by 1. Well, 2 and 3. I just need to make sure that the 3 is negative so that I get a negative middle term here. Okay, this is what I call the reverse FOIL method. Okay? So I have solutions then at x equals a negative 2 right there and x equals 3 right there. Okay? But watch how easy I can mess this up. What if I make that 6 a 5? Okay? That wasn't tough. I can still see my zeros on the graph. They've now moved a little bit closer to 0. This is inside of 3. This is inside of a negative 2. But what are they? If I go to factor this, I now need two factors of 5 that differ by 1. I don't know what those are. Okay, I'm kind of in a quandary to find those. So just that easy, I'm able to take apart this whole idea that we can factor everything and get the answer. It just isn't the case. We need another method to solve these types of equations which pop up in a lot of stuff. So we end up using what's called the quadratic formula, which I'm now going to flash up for you. Let me warn you ahead of time. If you haven't seen this thing, it could cause bleeding from the ears because it's very messy. But now that you're braced, I think you can handle it. This crazy negative b plus or minus the square root of the quantity b squared minus 4ac, all of that over 2a. Okay? That is a formula that will give us the two solutions to this general quadratic. The a, the b, the c come from these entries of the general quadratic. The a is the coefficient of the x squared, the b is the coefficient of the x, and c is the constant term. Okay? And your teacher will derive that for you. I don't want to do that here. due to time constraints. But it does tell us a bit about what's going on. Because of this square root, we could run into some problems, right? If this b squared minus 4ac business is positive, then the plus or minus here will give us two real answers. If it's 0, we're adding and subtracting 0. So we only get one real answer. And here's the troublemaker. If it's negative, then we've got that negative under the radical. That's a complex number, which we talked about last time. I'm not going to get any real answers. I'll have two complex answers. That would be the situation where things do not cross the x-axis at all. They're either floating, the parabola is either floating above it or floating below it, opening downward. The one thing I will point out is that if you average the two answers, that gives you the axis of symmetry. If I add these things together, the plus and minus negate each other. I get 2 of the negative b's, but then when I average, I divide by 2. And so I just end up with a minus b over 2a. And that's helpful to us as well because it'll tell us where the axis of symmetry, it'll tell us where the vertex is. And on a parabola, the vertex tells us either a maximum or a minimum. So in this particular case, let's walk through it. Negative b, right there, negative and negative 1, negative 1 squared, and then minus 4a, and there's c. And I think if I've done my arithmetic right, that becomes a 1. This would be a 1 plus 20, so it should be 1 minus the square root of 20 over 2 and 1 plus the square root of 20, quantity, over 2, which works out to be these two answers, which I alluded to just kind of inside the two previous answers. Okay, so that looks plausible. I think that's going to work. And it even tells me the axis of symmetry is at a negative b. Negative negative 1 is 1. 2 times 1 is 2. So there's my axis of symmetry, and it locates the vertex for me. So that's useful in doing max and min type problems. I feel like I ought to at least talk about one problem. So let's look at this one. We don't have a World Trade Center anymore. It was destroyed in a terrorist attack. But that was a huge building, and I remember when that attack occurred, there were stories about the debris falling and even people jumping out of the building to avoid the heat of the flames and things like that. And I remember thinking, wow, how long a fall is that? I mean, that's a huge fall. You know, it's a quarter mile. And I have no concept of that myself as to how long did it take 3 seconds to hit the ground? Does it take 30 seconds to hit the ground? I don't know. Well, let's do the arithmetic. The equation that governs this, and I don't have time to derive this, is a negative 16t squared plus initial velocity up plus the initial height. And I'm doing everything here in feet and seconds. So when I go through, I've got the negative 16t squared. The height here at the very tip top of this would have been 1,353 feet. And to get the answer, I just need to solve that for 0, which I plug into the quadratic formula. 0 here for the b, the coefficient of the t term is 0. And it turns out to be a plus and minus this over negative 32. One answer is negative. I don't want that answer. The positive answer is about 9.2 seconds. So that's a long time. Now, the one thing I'm not doing here because it's more difficult is I'm not taking into account the wind resistance, which would slow you down. But I have, on the other hand, calculated the fall from the very tip top of the thing, which would make for a longer trip. So really, when you kind of do the give and take, that was probably standard. And that's time to think. You know, that's kind of scary. I've got some summary pages here that I'll flash up that kind of show what we've been talking about.